Hello and good time whenever you're watching this video. Our aim today is to introduce some longitudinal modeling, and I will assume that you know already about structural equation models and how to draw a path diagram or to read a path diagram and how to do estimation with Bayesian estimation. Our major tools if we do any empirical science. Modeling in general means that I describe something I don't know, some distribution of my data, by a formal model that then describes in turn a probability distribution. And my model is really my set of assumptions. So if you do your model well, you shouldn't have any other assumptions than the model itself. Okay? And for longitudinal modeling, like for any other modeling, it's more an art than a science. I can show you some vanilla cases of how to do modeling and some specific frequent cases, but whatever your specific cases, your research topic that you are interested in, you will most likely have to create your own model. So it's a little bit like if you learn how to draw a painting of a tree. Yeah, I can generally tell you there's something like the bark and how to draw the bark of the leaves and these things, but your specific tree looks different than my specific tree, and you will have to do your own thing just based on the vanilla cases. The very first longitudinal model that you might look at is a latent change flow model. That's about as simple as it gets for longitudinal models. So we have one pre-test and one post-test. Yep. So we measured our participants exactly twice and did something to them in between. What we assume is that there is an intercept, so something like an ability they already had before they came into our lab, which therefore maps into the pretest. And remember, if I don't write anything on the arrow, it means that this is just a copy, so it's there's a 1 on this arrow. But of course, whatever the intercept is, it also goes into the post-test, right? Because whatever they bring into the experiment, they will still have after the intervention. We also assume that there is something like a variance here, a residual variance. So on top of the variance that they have, because humans are just different with what they bring in, they have some residual variance, which is the part that is not modeled in the latent part above, plus which includes probably measurement error to some degree. Okay, but we do assume that here's some variance that you might be interested in, so difference how people come in. And then, we also want to introduce a mean of the intercept, of course. So this would be the mean of the intercept. Then comes the real interesting part. We want to know the change. So if I do something with my participants, how do they change? So we've got a change variable. And the change variable obviously does not get added to the pre-test, but it does get added to the post-test. Yeah? Again, it has a variance and a mean. So, and done is our first longitudinal model. Yeah, it doesn't get any easier. So that is typically called a latent change score model. You've got the changes, which are have their own variance and mean, the intercept, which has their own variance and mean, and the residual variance, which gives a total of 5 parameters, though the model is just specified, and with that it will fit perfectly to any situation you have. It's just a re-expression of your actual empirical findings. Let's extend our latent change score model a little bit. So let's assume we don't have only 2 measurements, but in between, during the thing that we did with our participant, we measured them halfway through again. Okay? So we've got a pre-test as before. Pre-test. And we do have the post-test. Still in there. And in between, we've got whatever you want to call it. Yeah? Half-time test. Something like that. And the nice thing about this is, this changes, so we've got a new actual distribution of our data, but we leave the latent part, the actual part that we are interested in, the same as before. So we create an intercept here, a latent intercept, a latent change, and we again give the intercept and the change and mean and a variance. Variance of the intercept. And we also, as before, allow for a residual variance at the specific measurements. And observe that just as in the latent change curve model, I name these parameters the same, and generally if parameters are named the same, they are actually the same. Okay, so it's just one parameter that governs all three variables. I could change this if I want, depending on situations. But here I'm diverging from the vanilla case already, and I don't want to do this at this point in time. Let's see how these are connected. Okay, so this is the intercept. It's again what our participants bring in even before they start. And of course, we want this to be in every of our three measurements because we assume this is common within the participant. Okay, we also have no connection from change to the pretest, obviously as before, and we have a connection from change to the post-test. Now the interesting part is this connection here, and we do have a connection because after we did whatever we do to them halfway through, we expect that some of the change already ended up here, but not all of it. Yeah, we only want half of the effect of the change to be visible in this half point time. To do this, we add a fixed constant here, which is called, which is 1/2 in this case. And this is a latent growth curve model. Okay, fairly simple change, and we already have 3 observations. So, say a longitudinal study was running over 2 years, right? We have a pre-test, and after 1 year, after 2 years. Okay, so this is fairly vanilla, but I could do lots of things with it. Yeah, and I will not be able to catch exactly the point that you are interested in. So you have to understand it conceptually to do your own changes. But just to give you example what we could change, examples of what we could change, let me play around with it a little bit. So, for example, first thing I could do is I could lift the assumption that the variance, the residual variance, is the same over time. Yeah, sometimes that is a reasonable assumption. If I measure with the same instruments and I've got something which I don't expect to be varying differently on different times. But sometimes it's not, especially over longer longitudinal studies. Yeah, I've got a year between these two. A lot may have happened in between this year, which just changes the variance that people have on my measurement potential. So I can make it raise 1, raise 2, raise 3. I've got to be a little bit careful because this gives me a 3x3 covariance matrix of observations. So there are really 6 equations, if you want. Already I used up 5 variance parameters, right? So I'm running a little low. I can only add 1 more parameter that has to do with the variances in my model. A typical point where we want to spend this 1 parameter is to measure a covariance between the intercept and the change. Yeah, because we want to know whether people who start up high benefit more or potentially less from my intervention. Okay, now I've got 6 variance parameters in my model and 2 mean parameters. Of course, if I've got another point in between here, and let me add this. Which is x 1/3 and x 2/3 of my time. Again, influenced by the intercept and influenced by the change with a constant of 1/3 and a constant of 2/3. Raise 2, raise 3, raise 4. I've solved my problems because now I've got a lot of parameters that describe the variance. The more frequent I measure something, the more I'm able to refine my model and still be good with it, right? Although I probably don't want to put any more parameters in here. don't I? Maybe I do. Assume, for example, that I'm not quite sure whether my effect really is linear. So here I made the implicit assumption, or no, explicit assumption, because it's in the model, that the change, if I only look at 1/3 of the time, the change will act 1/3. Yeah, but that may not be the case for some interventions. They might, increase their steepness or decrease their steepness, either of the two or any other. So I may want to add something to this to describe, in addition to the linear effect, something like a quadratic effect, for example. So I could have a quadratic here, and again, I want a variance for this, I want a mean for this. Used m before, so let me use m here too. Okay, and again I want this connected with a single edge to the post test, but I do want it connected to the other two time points in a way that describes a quadratic increase. Okay, so this one is supposed to go into these quadratic. So 0 to the pretest, of course. Here it's 1/3 but squared. Here's 2/3 squared, and this is 1 squared. So now I've got a quadratic latent growth curve model, which means I can model something which on the latent level looks like this, like a parabola. Okay, so this is time. This is maybe your cognitive ability of our participants. They start up here, so this is the mean of the intercept. And then we train them by some way, or have them do exercise or whatever we want. And then we see that they actually, on average, increase in a quadratic fashion. And that's we can model with this model. And of course, here we might be interested in any of these covariances, right? So the covariance between change and quadratic. That could mean that someone who is steeper overall also has a stronger increase if there's a positive covariance. And we might be interested, running out of space for my arrows here, in the covariance between the intercept and the quadratic. Both longitudinal models that I've shown you now as a kind of vanilla examples are the latent change curve model and the latent growth curve model are based on the assumption that we've got a natural starting point, and from this on something happens, a process that we want to describe. That's of course not necessarily the case in all situations. So typically if you decide for a longitudinal model, the first thing we look at is stationarity. If a model is stationary, in a sense that we want to use it here, it's really like a weak stationarity, we assume that it doesn't matter where we start looking, we will always find the same distribution at this point in time and the same dependency between different points in time. Okay, so this is the concept we are after. So stationary means it's not important where I start looking, which is definitely not the case if I do something with my participants, like train them something. But it might be the case, for example, if I look at the interaction of different brain regions or of hormones, or of a long-time mood observation. If I observe the moods of the participants without doing anything, I just do some experience sampling, for example, then I won't expect that they are influenced by something that has a starting point and an end point, which I control, like in an experimental condition. Okay, so if I find non-stationarity, I'm probably well off with the latent growth curve model and its little brother, the latent change curve model. If I find something which is stationary, I might be more interested in measuring the dependency between time points. Okay, so here I don't write pre-test because there's nothing that it could be pre, but just x1 as any arbitrary point in time, and an x2, and an x3, and maybe more. And what I want to model between these is the prediction that I can make from any time point to the next time point. Okay, so I've got here a prediction. What does that look like? So I've got here a prediction, and here a prediction. And I always make the regression from the variable to itself, but on a later point in time. And this regression to itself is called an autoregression. So autoregression model. Of course, what I need in an autoregression model, again, are residual variances. Whoop. Because I assume the whole thing is stationary, my parameters here and here are named the same, because it's the same process wherever I look in time. And also this and this residual variance should be the same. Residual variance. However, for this first point in time that I start observing, I need a different parameter name, for example V0 for the first variance, because I'm lacking whatever came in here. Really something happened before x1, but since I didn't observe it, I need to capture that into the V0, so the variance of the first time point will be different from the others. But this being the same is part of the stationarity assumption. Okay, and of course I could have an x4, and it just looks the same. Ain't that nice? Yeah, I can do this as long as I want. The higher the alpha is, the higher the prediction power from one point to the next is. And that's typically what describes a process which is very stable. While if the alphas are all 0, it is still stationary in the sense that at every point in time the same thing happens, but 2 time points are no longer interacting in any way. So we've got something which is white noise. Yeah? So at every point in time we've got completely new normal distribution for our observations. Again, this is kind of the vanilla version of the autoregression model, but there are so many variants. Yeah, a very frequent variant that you will see is that people draw it like a latent chain here: x2, x3, and x4. And then take the measurement out of the picture. So make from every latent variable a separate measurement model, which also may include multiple indicators or different numbers of indicators at different time points. For practical reasons, for example, you measure the same latent construct with only one indicator at most times, but at some point in time you measure them with many indicators. So you can have different measurement models down here. And the advantage now is that you have a little bit of the residual variance, which I now term error here, which has only to do with the measurement itself, while the part that comes in here is a residual which also includes something that is part of the latent thing going on and will continue to the next point. Yeah, so if I've got a very high value here, it will be propagated to the next point. And so this is not propagated, this is propagated error. And again, I need to make the first one different to capture the missing error from here. I can make lots of other tricks. I could, for example, have different time steps in here. So let's assume that between x2 and x3, not 1 but 2 time steps happened. Yeah, we could say that all these measurements are daily. Yeah, so every time at 8 a.m. you are asked to fill out a small questionnaire. And 1 day is missing for practical reasons, or it might also be useful actually for the model in some cases. So what do we do then? Yeah, what happens is that really there's one measurement point in between. Actually, let me draw that. So we just add a measurement point in between. And we got our alpha here and our alpha here, but we got no measurement here. Okay, so we just don't measure this x 2.5 point. Yeah, platform 3 and 3/4, 9 and 3/4. You can have any point in between. Of course, you could omit this and just label these paths as alpha squared if your program allows. For example, Onyx doesn't allow this. With Onyx, you've got to do these too. But other programs do allow that, then you can just take out this dummy node here. Yeah, latent variable without own variance or mean is typically called a dummy node. just propagates the effect. But that works nicely. And this you can do in very, very, very big scale. Yeah, you can have multiple variables at once that are connected by a whole matrix, and then you can make continuous time steps in between with some modeling trick that you can find with Manuel Völkler's work, for example. Lots of different variants again, like painting a tree. So what we've got at this point in time are some non-stationary models and some stationary models. And of course, this is just such a small glimpse of possible models you could do, right? Including all their nieces and nephews and children and variants. And don't get me started. I want to show you one more model that you could use for stationary, which is much more powerful in general, but still it's just a more vanilla form, which is a latent differential equation. So, as you probably know, almost everything that we do is really a differential equation. Yeah, even if we do some non-stationary things like intervening in the process, we could look at it as something from the outside acting into the model and just changing autoregression parameters or something like that. And typically, if you have a first-order differential equation, that means that the change of something depends on the actual value of something. And that can be fairly well caught with an autoregression model. But for some processes, you have things where the second derivative depends on the actual value of something. Easiest physical example is a pendulum, right? Where the acceleration of the pendulum at any point in time depends on how high the pendulum is at this point. These things are second-order differential equations, and they happen also in psychology a lot. If you want to model something like that, doing it with an autoregression kind of model is still possible, but it starts to get nasty. And since the differential equation just means that the second derivative of something depends on both the first derivative and the actual value, why shouldn't we put this in a model? We can do everything in a model. Why shouldn't we? So let's do that. Okay, so I will have one thing here, which is x, one thing here, this is the derivative of x, and one thing here, this is the second derivative of x. And I say that the second derivative of x is predicted by the first one and the actual value here, b. And probably I will also allow for a covariance between these two, but that's more to capture whether my differential equation really captures the process well, or there's another dependency here which is not captured by the differential equation. Okay, so doing this on a latent level is cheap, but how do we connect it to actual data? Assume we've got a very long data set, like 100 data points for every participant. And now what we do is we cut them in little time chunks. And these little chunks of time, we, like for example, 5 measurement occasions describe a short part of the process. Okay, so we look at a photo, like an instant photo of the whole process. Okay, I will make this here. So these are 5 time points, and since I can cut my 100 time points of every participant in lots of little chunks of length 5, which is called the time delayed embedding, I create a lot of almost independent samples. Yeah, almost. There's a little assumption violation here because probably they're not completely independent. But I'm fine with that because there's a paper out there that shows that this actually could even lead to better estimates of the parameters. Okay, so these are our measurements. X, yeah, we assume that these are really like infinitesimally small time chunk. So X will just go into all of these. Yeah. Whoop. But it does change a little bit over time. So it's like a latent growth curve model, where this one here is a linear change. Yeah. And the linear change, in this case, we do symmetrically around this point. This point is 0. So what in a latent growth curve model is our initial point. And the other go here. And it goes -1 here, -2 here, 1 here, and 2 here. Where, just as a reminder, I wouldn't have to put the 1 because it's an empty arrow means 1, but for completeness sake, so that we can see it better, let me do it this way. Okay? So this now describes a linear change. And this one I want to describe the change of the change, which is the second derivative. And the second derivative of something which is assumed constant in this small time frame is actually the squared things here with an addition of 1/2. That 1/2 just comes in because the derivative of x squared is 2 times x. Yeah, it's not very important. But we have to put it in here, so it also goes here, and here, here, and here. And the labels I put here are just the same labels as here, but squared, and then half of it. So -2 squared, that's 4, and the half is 2. Then -1 squared, that's 1, and half of it is 0.5. +1 squared is also +1, half of it 0.5. And finally, the 2 squared is 4, and the half of it is again 2. Yeah, so if you look at these things, include the 0 in your mind, then if this one is the middle point, yeah, it's got 0. These two are at 1/2, and these two are at 4. So it describes a perfect parabola. Okay, so that is how we measure the second derivative. And we also want to add a residual variance. And in this case, because we assume that it's a really short time, and that we can really look at the value to be the same over time, we would probably prefer to take the same parameter for these residual variances here. Okay, so the model is well specified. We can definitely find a solution, typically fairly quickly, and there's even analytical solutions to this. And then, based on that, we can describe the result of our latent differential equation. Again, with a Bayesian estimate, preferably, of course. Okay, so that gives us an A and a B. Yeah, so the solution to this differential, or actually the differential equation up here. And based on that, we can look up equations for the temporal and based on these, we can look up the development of this thing here over time. And it will typically look something like this. Which you may remember from school is a dampened sine curve. That's a dampened oscillation. If the A here is 0, there's 0 damping, and it will just be a sine curve. And the frequency of the sine curve is controlled by B and by A. And again, if A is 0, then it would just be controlled by B, of course. In fact, I can write this plot here as an equation f of t, this being t here, which is e to the at half times a cosine, and the cosine is of square root a squared quarter minus b times t. So typically you can also describe this curve as something which comes a little more understandable than this hard equation in two numbers, which the first one is the half time. So this is the time it takes until the amplitude of the sine curve is only half as strong as it was initially. And this one is 2 over a times the logarithm of 1/2. And the second part we might be interested in is how long it is for a whole cycle to repeat. So the cycle time. And the t of the cycle is given by 2 times the square root of 4a squared minus b. This is really just solving this equation, so it's not high mathematics. But these two numbers, these two times are easier to understand, of course. So you could write in your paper something like, I fitted my latent differential equation and taken the maximum a posteriori estimates for A and B. I figured that the expected cycle time for this hormone is 2.3 days, where a strong excitation of the hormone will take about half a day to reduce to half its strength, something like that. So that was really quick. So we went through some possible models that you can do for longitudinal modeling. Very simple 2 observation model with latent change score model, which just measures the change between 2 things. Its extension to a latent growth curve model, which has more than 2 things, but other than that, it's just the same thing. And 2 models that we could use for stationary time series, or 2 family of models, I should say. The autoregression family and the latent differential equations family. Again, 1 million of variations, and of course this is by far not exhaustive. There are so many more longitudinal models you may want to use, but probably with these 4 you will survive in 99% of the cases, right, with some variations of these 4. If this was too fast, which I could understand, I may hint you to other videos I've got on the web, where the same things are described just with a little more time and smaller steps. You may want to watch those if you feel not familiar with these. If this was a review for you, all the better. Wonderful. Thanks a lot for listening. See you later. Bye.